Hi folks, welcome back to Physics with Captain Rod. The purpose of this video is to go through an example of how to apply the work energy theorem. So in the example we're looking at, we've got this cannon here, and this cannon will fire this cannonball at a speed of 500 meters per second. All right, we're going to imagine it does so in such a way that it makes a 20-degree angle with the horizontal, and what we're going to try to calculate is the maximum height reached by that cannonball. So the trajectory of the ball, if I did like the motion diagram for this problem, the trajectory of this ball is going to look something like this, although it's going to probably go many meters. All right, so it's important to note we're going to get like this parabolic type motion. At the highest point, it's going to be here. It's important to note that the velocity at the highest point would be horizontal. I'm going to call the velocity here v1, the velocity here v2. Right? Now, we're going to talk about how to apply the work energy theorem. Before we do though, let's talk about why would we apply the work energy theorem. All right, so when we look at this problem, recognize here that we have a significant kinetic energy. And as the ball travels through the air, it's moving higher and higher and higher. So its potential energy is increasing. At the same time, it's moving slower and slower and slower, so its kinetic energy is decreasing. If I keep going with this, for the rest of the problem, when it starts coming back down, its potential energy is going to be going down, and its kinetic energy is going to be going up. So because we have kind of a shift between potential and kinetic energy, that is our clue that the work energy theorem is probably a good thing to apply here. Right? When applying the work energy theorem, always label our two positions. So I have a position here. I'm going to call this position 1. Here's our second position. I'm going to call that position 2. I've already labeled the velocity vectors accordingly. The v1 is the velocity at position 1, v2 velocity at position 2. Now, we know v1. v1 is 500 meters per second. What we don't know in this problem is v2. This guy here is not going to be 500 meters per second. I'll talk a little bit later about how we're going to deal with that. All right, so we've drawn our picture, labeled our points 1 and 2. Then we write out the work energy theorem. PE1 plus KE1 plus work from 1 to 2 equals PE2 plus KE2. All right, now anytime we're dealing with potential energies, we need a place to measure them from, so that means we need to put a datum in the problem. I'm going to go ahead and do that, and I don't know why, but I like blue datums. So I'm going to go ahead and put our datum, I guess I'll just go ahead and put it right at the initial height of the cannonball. So there's our datum. Now, normally I put a datum on the ground, and we can do that, and it's perfectly fine. This distance looks like it's about a couple of meters. It turns out that height we're going to deal with, I'm sure it's going to be many meters. It's going to be a large enough number that this 1 or 2 meters is not important, but I'm going to go ahead and put our datum right there. So there is our datum. We're going to measure potential energy from that point. Right. Now, as we go through this, right, our PE1 terms, so gravitational potential energies, are MGH terms. Here at position 1, there is no H, so that guy is going to be 0. KE1, right, 1/2 mv1 squared. The work term, I'll go back and talk about that later. I always like to do the work terms last. PE2 is going to be an MGH term. The H is going to be this height. Right there. Should be labeled in your picture. We shouldn't have anything, velocities or positions in our work energy equation that's not labeled in our picture. KE2 is going to equal 1/2 mv2 squared. All right, let's get back to that work term. All right, so work is force times distance. A free body diagram, always a good idea when you're dealing with the work energy theorem. So if I imagine this particle just somewhere along this path, the only force that's really important right now is the gravitational force, and that's going to be down equal to mg. If I decided to include air drag, that force would be to the left. Air drag, like friction, always opposes motion, but I'm going to assume that one away for this example. I don't think it's going to be that important of a force. And that's it. There's nothing else in contact with that ball, so that is the only force. Now, there is work done by this force as we move from 1 to 2. Remember, work is force times distance. only the component of the force in the direction of motion does work. All right, so long story short here, the only thing that matters for this force is this displacement right here. The left-right motion does not matter for this force. Even if we tried to put a work term in, the force is mg, the distance is h, and the work term would be negative because between position 1 and 2, the vertical displacement is up, not down. And you'll notice that the velocity, the mg is down and that displacement was up, so therefore the work term would be negative. So if we put a work term here, it would be minus mgh. However, I take note, we already have an mgh term sitting here. We have already taken this force into account. If I were to put a work term here for it, we've taken that into account twice. So I'm going to go ahead and just put a 0 there. We considered all forces. The only work term was for gravity, and that's already taken into account right there. And I'd like to take a moment and point out that a positive mgh on the right is mathematically equivalent to a negative mgh on the left. All right, so we're done. We're done writing our equation. All forces taken into account. Usually the next thing I do is kind of glance the equation over. I'm going to take note that we don't really need the zeros. Also notice there's a mass in each term. So I'm going to go ahead and divide that mass out. What we're going to have is a v1 squared over 2 is going to equal gh plus v2 squared over 2. And all I've done is taken this equation and kind of boiled things away. We don't need this, don't need this. Mass divides out. All right, now I'll start dealing with that v2. And if we think back to dealing with projectiles, one of the things we would typically do with a projectile problem is take the velocity vector and break it into components. I'm going to go ahead and do that now. So there's the x component, might look something like that. The y component would look like this. The x component's to the right, the y component's up. So this I would call v sub o in the x direction. This one I would call v sub o in the y direction. Now this interior angle is a 20-degree angle. Therefore v sub ox is equal to the initial velocity, which is 500 meters per second, times the cosine of 20 degrees. And we get a numerical value out of that of, what did I get here? 470 meters per second is what I got out of that. Now the reason I calculated the v sub ox, well, when we look at this force, right, it only has a y component to it, or a vertical component. It does not have an x component. And that means that horizontal velocity component is going to stay constant in this problem because there's no force to change it. And I take note that here at position 2, the velocity is purely horizontal. So v2 is equal to 470 meters per second. So I'm going to go ahead now and just put in values to this, and I'm going to put a little NCU for note consistent units. So this is going to read 500 squared over 2 equals 9.8 h plus 470 squared over 2. And I'm going to take a moment here to solve that for h. Let's see, we would subtract the 470 squared over 2. We're going to have 500 squared over 2 minus 470 squared over 2 equals 9.8 times h. And if you go ahead and calculate this, get a calculator out and run that, divide it by 9.8, I get 1,484 meters out of that. So this thing's going to end up pretty high. Now, we ignored air drag, and that's perfectly fine. At this point, just recognize that this is basically an estimate, just to give us an idea. I mean, air drag probably is a reasonably significant force here, but the purpose of this problem wasn't how to take every detail into account. The purpose of this example was just to go through and demonstrate how we apply the work energy theorem. So again, let me recap that. You always draw your system at the two states here, state 1, state 2. Make sure they're labeled. Right? 1, 2. Draw all relevant velocity vectors and give them names. Draw other relevant geometry like the height here. Write out the work energy theorem like we did. Anytime you're dealing with potential energies, you have to define a datum like I have. Right? Then just go through it term by term. The potential energies will be MGH terms. Now later on in my course, we're going to talk about other potential energy terms. The gravitational potential energy is the first potential energy that people usually learn about in physics, but again, there's more. The kinetic energy terms are going to be 1/2 mv squared terms. Right? Work terms are going to be force times distance. You typically look to your free body when dealing with work terms, and you have to make sure that every force has been taken into account. And that's pretty well it. You write out the work energy theorem, go through it term by term, put in values, and typically you can find something out of that. So hope this video helps demonstrate how to use these concepts. Have a great day.